Sorry, I'll just press to record. Okay, well, hi everyone. Welcome to today's meeting, which is from the Atomic Spectroscopy Group. And today we are organised a seminar on F is for food, following our A to Z series. This is our 6th virtual meeting. My name is Jackie Morton, and I've helped to organise this virtual meeting on behalf of the Royal Society of Chemistry's Atomic Spectroscopy Group. We have 3 speakers for you today: Sonalika Jain, Andrea Raab, and Panayot Petrov. The format of the meeting will be that each presentation will run sequentially with speaker one after the other, and at the end we'll collectively answer any of your questions. Please feel free to type any questions in the chat and address the host only. We will try and coordinate the responses at the end of the talks. If you wish to specify the presenter you want to address your question to, that's okay too, and that would be useful. If I can ask everyone to make sure, because I seem to have not done it correctly, to have their cameras turned off and their microphones off also. Okay, so our first speaker today is Sonalika Jain from RSSL, Reading Scientific Services Limited in the UK. Sonalika holds an MSc Chemistry with a year in Industry from Imperial College London. And with over 5 years of experience in analytical science, Sonalika has worked in developing biosensors for single molecule detection using nanopores and advancing the field of nanoparticle characterization using specialized techniques. She currently works as an analytical scientist specializing in elemental analysis in the metals department at RSSL to support both the food and pharmaceutical industries with their testing and regulatory requirements. Sonalika, welcome today. Thank you for agreeing to give your presentation. And if I could ask you to share your screen and begin your talk, that would be excellent.
Great, thank you very much, Jackie. Let me just share my screen, and if you could just confirm that you can see that.
Yes, that's perfect.
Lovely, okay. Okay, so good afternoon, everyone. Thank you, Jackie, for inviting me to speak at today's event. Pleasure to be here along with so many other experts in this field and spectroscopy in general. So today I'm going to be talking about elemental testing in food, the good, the bad, and the tricky. So as an overview, I'll be going more into detail of why we do elemental analysis, talk a little bit about sample preparation, then go on to giving some insights into performing the analysis using various techniques, and then close off with some food for thought. All right, so before we dive into the technicalities and the science, let's talk a bit about why we even care about quantifying the amounts of different elements in what we eat. Well, to me, if I eat something and I find it delicious, that's all I need, right? Well, actually, let's take a step back. So think of a family sitting down to dinner together, be it Thanksgiving or Christmas, you choose it. They have full faith in whoever cooked their food. There's no doubt of safety or reliability. Now, on a larger scale, apologies. Jump the gun, yeah. Now, on a larger scale, this confidence translates to the food and beverage industry that supplies communities worldwide. When the same family goes shopping to buy their favorite products, they depend on the food industry for the safety of those products and are very much confident in it. Naturally, then, the industry has a huge responsibility to fulfill. So how do we ensure that consumers enjoy and return to the products as much for taste as their promise of safety? This is where the role of elemental analysis becomes invaluable. Now, there are 2 overarching uses of elemental analysis in the food industry. First one being nutritional perspective. So looking at minerals, essential minerals in food that help the body grow and develop, for example, calcium or potassium, but also looking at trace elements that we require in smaller quantities, iron, zinc, manganese. And I believe Dr. Andrea Raab will talk more about trace elements in her presentation. The second part is identifying contamination in food materials, specifically arsenic, cadmium, lead, mercury, which I'll come back to in a bit. Now, food companies may want elemental analysis for a various number of reasons. So, for example, if they're changing over their raw materials or switching their recipes, or it might be that they're changing manufacturing processes or internal analytical procedures. It might be that the companies need to conduct some claim substantiation, or more often than not, comply with new legislations. Now, most countries have their own regulatory bodies that oversee food quality, and particularly metals in food. So for example, the FSA here in the UK, EFSA in the EU, and FDA in the US. Now, the compliance is mainly around heavy metals, but a lot of it is also driven by consumer needs, for example, sodium reduction. The food landscape is an ever-evolving one. It's very much driven and shaped by us, the consumers, and we're becoming more and more aware and mindful of what we're eating. We look out for the salt content, whether they are fortified minerals, or if the health and nutritional claims in a product are actually what they say they are. And as a result of this awareness and legislative compliance, there is a big piece around transparency and food labeling. Legislation dictates that nutritional information should be clearly detailed on food packaging, and this is where validating these claims using atomic spectroscopy becomes ever essential. Now, I mentioned metallic contaminants earlier. These elements generate concern because of their toxicity, especially when they start to accumulate in the body over time. And although they may be present at low levels in foods, they can sometimes start to add up when we start combining all the foods that we eat. These metals enter your food chain through the air, water, or soil, either due to natural geography or human activity, be it industrial or agricultural. We need to, however, consider the levels and forms of these elements in which they exist in, whether they're bioavailable or not, to really evaluate their toxicity. For example, when we talk about arsenic, it's the inorganic form that we're worried about. In the organic form, the arsenic atoms are firmly bonded in the carbon network, so they're very much unavailable for bonding with the biomolecules, which is not the case with the inorganic one. The toxic form of arsenic is usually present in high levels in groundwater, and as a result, they seep into your rice and crops, which then come to us when we eat these crops. And I'm sure Dr. Panayot Petrov will be talking more about this in his presentation as well. There are strict regulations for arsenic in drinking water, almost less than 10 ppb or even lower. We'd ideally need to do some speciation to break down how much of the quantified arsenic in the food is actually inorganic, but the typical approach would be that, well, we measure the total content of arsenic and assume it's dominant in one form in the inorganic form. Chromium. So toxicity depends on its oxidation state. So chromium-6 is more toxic than chromium-3, and it's also more readily absorbed by inhalation and oral routes. But chromium-6 is also not very stable, and it's quickly reduced to the lower oxidation states. Mercury. So mercury is present particularly in seafood. Mercury accumulation in fish is well known. There was a very famous case in the 1950s in Japan where inhabitants were exposed to high levels of mercury in the form of methylmercury. And this led to a disease called the Minamata disease, named after the location. And this happened because there was bioaccumulation of mercury in the fish as a result of contaminated industrial wastewater, which of course then translocates into humans. Tin. So leaching of tin from canned foods is known and it's regulated to a certain extent, but tin is not hugely toxic, depending on the quantities. Lead is pretty much ubiquitous as a result of historical use and natural occurrence, and we're exposed to lead through food, drinking water, air, soil, and dust. And there's actually a law that was passed in the US called the California Proposition 65, which requires businesses to clearly warn inhabitants of significant exposure to toxic chemicals. And essentially, lead is listed as one of these chemicals to which exposure is virtually unacceptable. Cadmium is an interesting one, as although it's a toxic heavy metal, there isn't much mention in regulations. It's mainly found in small quantities in fertilizers and through atmospheric deposition. Now, this is a good example of how we really need to consider the correlation between risk to health, but also risk to exposure. Right, moving on to sample prep. Now, optimal sample prep is the first step to successful and reliable determination of the elements that you're looking for in food matrices. The advantage of elemental spectroscopy is that the preparation is fairly standard once we've answered some questions. There are times when, of course, some method development is required, especially when you're talking about some more complex matrices. Let's take a look at some of the factors and questions that we should be asking. First of all, what elements are required? Are we looking at volatiles or non-volatiles? What about the analytical technique that will be used? Are we using a technique that has very low matrix tolerance or high matrix tolerance? Does the analysis require certification, such as UCAS accreditation? If so, we might need to follow some specific procedures. Is the material soluble or reactive? So most food products will have a matrix made up of a mixture of carbs, proteins, and fats. And having an idea of reactivity will really help us to appropriately and safely choose the reagents that we're using. And of course, select the most time-effective sample prep method. What about homogeneity of the material? Are we dealing with, let's say, a cookie with nuts and chocolate chunks unevenly distributed? Or are we dealing with fine milk powder? For solid heterogeneous samples, we would need to blend them more often than not using liquid nitrogen to freeze them first. And this will help us make a representative sample as homogeneous as possible. What about the expected levels? Are we dealing with parts per trillion, or are we dealing with percent levels? Now, the beauty of food analysis is that we can already have a rough idea of what's in there from previous label claims, literature sources, and most importantly, the inorganic element section in the McCants and Widdowson's The Composition of Foods. Now, ashing is a well-established nutritional testing method, especially when we're looking at high levels in assays. We can report the ash value as a general total mineral content, and essentially we heat up the sample in a muffle, burn off most of the carbon, and you're only left with non-combustible ash, which is then analyzed for its elemental composition. Generally, we'd be using quite large sample sizes, so from 2 grams all the way up to 20 grams, which gives us a good representative amount of the sample. Microwave digestion is also a great technique. It's great at digesting out the organic content, removing the carbon, but you're using a much smaller sample size. So it's great when you've got only a little bit of sample available, but then if you want to consider whether or not you're getting a fair representation of your sample, that needs to be thought about carefully. Samples are subjected to high pressure up to 200 bars and high temperature up to 220 Celsius, although most samples would probably digest around 20 bar and 180 Celsius. And this leads to a complete breakdown of the food matrix. It's very useful for trace level analysis in volatiles such as mercury. We typically use nitric acid, but for matrices, for fatty matrices, to increase the oxidizing power, it would be really helpful to use hydrogen peroxide. But we need to be really careful with the reactivity. For example, if you're analyzing pure oils, you need to be careful as they can react explosively with nitric acid. So it would be critical that in this case, you use small sample sizes, gentle digestion conditions, and even use peroxide from time to time. Now, direct analysis is very rare, and it's only used in the case of drinks. But if your drinks have a high content of sugars, dilution becomes important so that you don't overload the torch in your instruments with carbon. So selecting the correct type of technique is key to achieving maximum sensitivity, reliability, and accuracy of your measurements. Each technique poses its own strengths and limitations, of course, and these need to be evaluated carefully. If you're looking to purchase an instrument, it's important to give some thought to sample throughput and productivity, how easy it's to operate, and last but not least, the costs associated with the instrument and all the accessories. When you already have a range of instruments, which is the case where I work at RSSL, the 4 most important factors to consider are which elements you're analyzing, the associated sample prep, the expected concentrations, and of course, the instrument detection limits and how low they can analyze. So the best detection limits are exhibited by ICP-MS, meaning that samples with extremely small concentrations, low concentrations of analyte can be analyzed. It pretty much boasts the lowest detection limits. What's more, both ICP-MS and ICP-OES are multi-element techniques, and they can detect around 70 plus elements per sample per minute. For ICP-MS, interferences from polyatomic species and the matrix can be challenging, and many of these can be overcome by using specialized gases and mass shifts, let's say if you're using oxygen. Otherwise, ICP-OES is always an option, depending on the levels. On the other hand, you've got flame atomic absorption spectroscopy, which is a very selective single element technique and has short acquisition times, meaning that it is suitable for analyzing large numbers of samples. It's also more robust to higher matrix content. You've also got graphite furnace, which is an excellent option for sub-ppm level analysis as well. Now, let me just take a moment to highlight another very interesting capability of multi-element techniques like ICP-MS and ICP triple quad in particular. And that is the elemental screen of up to 70 elements all in one go. Now, this is very useful when we want to have a snapshot of the elemental profile. A note on the preparation, however, when you do analyze for so many elements, you typically divide them up into 2 groups for preparation, depending on the compatibility and interactions between the elements. So one of the groups would be compatible with nitric acid, and the other group of elements are generally compatible with hydrochloric acid, typically the platinum group elements. Now, screens are very useful when it comes to investigational purposes. For example, if a client comes to us with a problem with tainted food samples, we can easily analyze a tainted sample against a control and identify which transition metals are imparting the color, for example. Another interesting application is looking at food authenticity and adulteration. Now, that's a big one for the industry because food fraud can not just blemish a company's reputation, but more importantly, deceive and potentially put consumers' health at risk. How do you know whether the spice that you pick off the shelf is actually what it claims to be or where it claims to be from and not a cheaper alternative? The elemental profile of a food product will very much depend on the geographical origins of the ingredients. So by quantifying the ratios of certain elements, we can very cleverly identify whether a product has been tampered with. Okay, so I'm going to talk a little bit about some interesting watch-outs when you're analyzing for metals. By no means is this an exhaustive list, but just an indication. So I mentioned sodium previously in the context of sodium reduction, so it's paramount for various reasons. Sodium wavelengths are very sensitive. So when it comes to analyzing sodium by AA, we'd end up using a wavelength that is a lot less sensitive so that we can avoid doing massive dilutions during the sample prep stage. Another neat way of slashing off intensity is to use SPDV ICP OES. And you'd use the radial mode instead of the axial mode. It's basically a different viewing mode for the plasma, which is specifically designed for measuring easily ionized elements, such as sodium. Now, on the flip side, you've got something like phosphorus, which has extremely low sensitivity, and so is challenging to measure. So depending on the levels, it's probably best analyzed by either ICP OES or ICP triple quad. Toxic elements. So I spoke about metallic contaminants, particularly arsenic, cadmium, lead, and mercury. As we'd expect them to be present at low levels, triple quad or MS would be the best option. Generally, heavier metals are better analyzed by MS as they have very few interferences. The lighter ones are trickier, and so OES might be a better option. It's also important to note that although ICP-MS is the most sensitive, it's also closely matched by a graphite furnace, which also has the added advantage of being more robust to higher matrix content. So infant formula is an interesting one because it has very strictly controlled mineral content and metallic contaminant regulations, given how delicate the development of babies is at the very start. Regulatory authorities are keeping an eye on baby food manufacturers more than ever now, especially after cases this year raised alarms because heavy metal content exceeded permissible levels, leading to high risks of neurotoxicity. Just a few months ago in August, the EU tightened and lowered the permissible levels of cadmium and lead in infant formulas. I've highlighted iodine and lead here as key elements, but really there are over 10 elements or so that are carefully controlled. So there are some elements that are a bit tricky to analyze, but if we know how to deal with them, then they won't catch us out. Mercury and boron. So boric acid is used as a preservative in foods. Both of these elements are quite sticky, meaning that they lead to a lot of memory effects. And if you don't introduce enough washes between your sample readings, then there is a risk of getting false positives due to carryover. Also, mercury is volatile, so you need to take care when you're doing the sample prep. Aluminium and silicon, they're both very light elements, and so they're pretty much plagued with interferences when it comes to using ICP-MS because they have a lot of interferences from the atmosphere. So OES might be a better option. When it comes to iodine and bromine, so they require special sample treatment that's different to the ones that I mentioned earlier. They need to undergo thermal extraction using alkaline media, such as TMAOH, purely due to stability reasons and minimizing loss. Titanium dioxide is an interesting one. So it requires HF digestion, so you have to be careful in terms of health and safety. But it's a different story when we start talking about measuring titanium content in nanoparticulate format, which is how most titanium dioxide is used in the food industry, especially when it comes to brightening products. For this, a very special application of ICP-MS needs to be used called single particle ICP-MS, which, as the name dictates, essentially measures 1 nanoparticle at a time. A lot of my work is centered around this, and it's a fascinating area if you do get a chance to look more into it. Okay, so, oh, sorry, there you go. So as we can see, the food industry holds a very special place of public trust within consumers, and we trust that the food we buy and eat every day are both delicious and safe. Many products go through continuous redevelopment and improvement based on consumer demands and needs, be it sodium reduction or mineral fortification. Regulatory authorities continue to work on ensuring that the right limits are set for various metals, and these limits tend to become lower and lower, making it more challenging to detect and quantify the metals. The FDF recently shared a draft regulation to lower the maximum level of arsenic permissible in various foodstuffs. So it's a given that atomic spectroscopy needs to keep up with these legislations. Moving ahead, the food industry is slowly entering the space of synthetic food as we navigate through food security and supply concerns. It'll be interesting to see how the regulations that emerge as a result of this require and call for elemental analysis, especially as transparency and labeling will be absolutely paramount in gaining consumer trust. As food supplies become more and more complex as well, it's critical that we fight food fraud and authenticity issues. And this is where elemental spectroscopy is a very, very powerful technique as we tool, as we saw before. The food industry and analytical communities are also seeking to create more advanced technologies that are possibly portable and serve as inline rapid methods to catch out food fraud at a very early stage. Now, food manufacturers won't always have the option to invest in state-of-the-art capabilities. And so analytical labs are and will continue to be key players in supporting the food industry with its testing needs to solve imminent challenges and ensure that the consumers get the very best. So if you have any more questions, I know we're taking questions at the end of the presentation. My colleague couldn't be here today, but if you do have any questions during the session or offline, either of us would be happy to take them. Thank you very much.
Thank you, Sonalika. That was a really nice overview of what's involved in elemental analysis in food. That was really lovely. Thank you.
Thank you.
Can I remind everyone that you can use the chat function for questions, or if you're feeling up to it at the end, you could share your screen and we'll unmute and you can ask the question yourself. Sonalika, can I ask you to turn off your camera and thank you very much. And so our second speaker today is Dr. Andrea Raab from Karl Franzens University in Graz in Austria. Andrea studied at the University of Regensburg and the Technical University of Berlin, and she undertook her PhD at the Hahn-Meitner Institute in Berlin, working on separation and detection of metalloproteins in serum and whole blood using elemental detection. Andrea then spent 20 years as a researcher with the Trace Element Speciation Laboratory in Aberdeen, and is now working as a researcher at the same consortium of Tesla at the University of Graz in Austria. And it's our pleasure to introduce her today. Okay, so Andrea, you should be able to share your screen.
Yes, I'll try.
Super.
Do you see it?
I see you.
You see me or you see the screen?
I see you.
Me, okay. Sorry. Is it now?
It's okay. Oh, there we go. That's perfect.
Good.
Okay, thank you very much.
Thank you very much for the kind introduction, Jackie, and for the invitation as well. I think we've spoken quite a few times about it.
Sure. Andrea, can I just get you to check your volume on your...
I'm sorry.
Brilliant.
Now better?
Perfect.
I always forget it.
It's okay.
I'm going to share with you just today some of our results from a study we've done some time ago on natural food supplement products. Let me start with what I'm going to talk about, a little bit about the background about nutraceuticals or food supplements, our samples, and a couple of other ideas I had there with regard to sample preparation and some of the results, and then a bit of arsenic speciation. Food supplements, nutraceuticals, that is a very, very large group of materials, pills, liquids, tablets, whatever you want, which is available on the market, mostly comprising vitamin and mineral supplements. That is the major group. Amino acids, prep and probiotics, some essential fatty acids in fish and krill oils, which are pretty high, have pretty high sales. Other botanicals like algae, microalgae especially, and garlic, and some others depending a little bit on the region you're living in. By law, they are foodstuffs. They are not controlled by drug agencies. And so they don't have to be tested for effectiveness and safety. And they are marketed as an addition to a normal diet, which are supposed to contain nutritional compounds with nutritional or physiological effects. There are quite a few things which I just took randomly from the internet. Garlic helps to maintain healthy heart circulation. One other one says supports eye health. So some of these claims in there are not necessarily that what is really a good thing for people who don't know about it, who are not really into it, because they claim things which are not necessarily proven, even when they are not supposed to claim them. The sales, as you can see, they were up quite heavily in the last year, in Europe especially. It was 5% or so up. So it's a large portion of the population which takes them. And due to the fact that many of these materials are plant or animal derived, the element content may vary quite significantly between the batches. And since the elements are food regulated, the supplements are under the food regulation, they are not very strict. Some elements are not regulated at all. As you can see in Europe, for example, there is no level for arsenic, either total or inorganic arsenic. And as well in the US, the nutraceuticals are not yet really regulated. There is a recommendation to be below a certain amount, 15 milligrams total arsenic per kilogram material. Cadmium is 0.5 milligram and lead is 1 milligram per kilogram. When the tablets, liquid or whatever is taken in daily with less than 10 grams of that material, then these values from the USP are recommendations. So what have we done in our study? At the time we had analyzed some plant-based materials, garlic and algae preparations, especially because they are have relative large sales in Europe. Then fish oils, fish and krill oil preparations. For most of the elements, we've done a digestion, just like Sonalika just said, with concentrated nitric acid, some of them concentrated nitric acid peroxide and the microwave, just box standard digestion. For the plant-based materials, it was pressureless, and for the oils, it was a pressured microwave system what we used to get the oil matrix to disappear, so to say. The elements, iodine and bromine extraction, it was just mentioned, they need a special treatment. They were extracted alkaline. In our case, we did it with ammonia and Triton at room temperature because we wanted especially the iodide and iodate and the bromide. And then we had some extraction done for the determination of inorganic arsenic using diluted nitric acid and peroxide, and heated the whole solution in using a microwave. That was done not to destroy the oil matrix in the fish and krill oils, but just so simply to extract the inorganic arsenic or the arsenic masquerading as inorganic arsenic after this treatment into a water phase, and then remove the oil phase before measuring the inorganic arsenic. One thing what hadn't been really mentioned massively so far is contamination risks, and that's what I want to put a little bit focus on here. Another list in the lab is a risk for all elements because he or she may contribute all elements which are around to the sample. Dust in the lab is as well something what is of a problem. Chemicals which you use to make your samples, to prepare your digests, can as well be vials. When you clean them beforehand, before you use them, make sure you don't put your finger into them afterward during drying. I've had that in the past. It was very funny when someone did that to me, or to the vials I've used better. And then some of the elements may get lost because they are volatile or adsorbed onto the plastic, especially in very low concentrations. So I always keep that in mind, that this is not contamination, but the opposite of it, and you might lose your elements. And the other thing with regard to quality control, especially when doing external calibrations, keep in mind the range, especially in the low concentration range, that when your samples are down there, that you keep a special eye on it. Salomon et al. Has published there quite a while ago a quite good paper, in my opinion, about that. And another thing what I've noticed is sometimes it's forgotten that the calibration blank isn't equal to procedural blank, but the procedural blanks are of course important to check the contamination of chemicals and vials what you use. And when measuring with an ICP-MS or probably as well with an OAS, I don't do much of that. Don't forget to add an internal standard, a suitable one, for drift corrections or corrections of matrix influences, and use a CRM, or better, more of than one. Why more than one? The number of elements certified is quite often limited in the individual material. For whatever food you want to analyze, food matrix, there might not be the exact matrix available as certified material. And the concentration ranges as well can vary, especially when you use matrix CRMs which are not correctly adapted from this or the same matrix as your sample, what you want to measure. In CRMs, usually the certified uncertainty is represented at 95%. And that was a range of CRMs we've measured. Down at the x-axis, you can see how often each one was measured. That was now is an example of iron, which was measured with an ICP triple quad on 56 using oxygen mode and hydrogen mode, or hydrogen mode, and both gave more or less the same results. But when you look a bit more carefully at it, you notice that all of them really fit nicely here together, so measured and certified values, but the olive leaves. They were treated exactly the same as the others, but they didn't really fit in. When looking at another element like manganese, the olive leaves is as well out. But in this case, the measured value is higher than the certified value in comparison to the iron, where the measured value was lower than the iron. So there is something which might be a matrix effect or something specific to olive leaf CRM, which we couldn't compensate for with our measurement method. Just keep that in mind when you do this kind of thing, that better check it double or triple. So our results, the general element content in the samples, we had about 6 algae supplements, 10 garlic supplements, 15 fish oil and 10 krill oil supplements. And I've set all these values now relative to the fish oil content, because fish oil was in all elements the lowest. On overall, algae contain the majority compared to all the other nutraceuticals. Algae contained most elements, especially in the non-essential region. Non-essential were all the toxic ones, plus the ones you normally don't talk about significantly, like uranium, antimony, aluminium, boron, etc. And then krill oil contained quite a lot as well of these non-essential elements, whereas the essential elements were highest in the algae when you consider it as milligram or microgram element per kilogram material. When you consider now daily intake, the picture shifts somewhat. The essential elements are still in the algae are still the highest, followed by garlic. But the non-essential elements are going down. It has something to do with how the daily intake is calculated. So fish oil generally is the lowest with regard to element content. Essential elements are predominantly in the algae and the garlic, whereby garlic is significantly lower than the algae, and fish and krill oil don't contain much. And the non-essential elements are algae, krill oil, garlic, and then fish oil. One of the elements I've picked out to show a little bit more in detail is iodine. It's essential for the thyroid hormones. And the intake is determined by the content of the food. Marine sources principally contain more than dairy and others. And in Europe, some of the food categories have to be supplemented by law, especially salt here on the continent, and at least in the German-speaking areas. Low intake isn't good for you. High intake isn't good for you either. So a healthy balance has to be found between these two levels. What we found in our supplements, that is now calculated microgram iodine per intake per day using the recommended dose from the manufacturer, which was written on the label. There are 3 algae products which are above the recommended daily intake. They are kelp-based. All the others are significantly below. What I personally expected when we started off this experiment, I thought fish and krill oil certainly go through the roof because they are marine-based. So I expected there significantly higher amounts of iodine or iodine-containing compounds in there, but that wasn't the case, at least not anything what we could extract using our method. Another element pair I've chosen to show you is the selenium and the molybdenum. Selenium is essential as a specific antioxidant enzyme, and molybdenum is as well required for specific enzymes. In Europe, generally, the selenium status of people is suspected to be low. Molybdenum isn't unknown. Selenium, we have not found significant amounts, really. One of the algae products and one of the fish oils, which was supplemented with some selenium, were the highest, with about 10 nanograms selenium per day. What that taking that tablet would contribute to your selenium intake. But when you consider that their recommended daily intake is 55 micrograms, you are not contributing much by taking a tablet of fish oil or algae. With molybdenum, the recommended intake is as well around 45 microgram per day, and as well the intake through these kind of tablets is not contributing really significantly to it. Even the algae are the highest ones are pretty low still in comparison. That is less than 25, respectively 10% of the recommended daily intake. And interestingly, molybdenum is nearly absent from all the krill oil preparations and practically non-detectable in any of the fish oils. That probably has something to do with how these fish oils are produced during prep cleanup of the fish oils. Probably the molybdenum is taken out just like iron, copper, and zinc. This process seems to remove most of the trace elements. So to summarize, for the essential elements, the daily intake is mostly below the recommended daily intake. And there are a couple of algae-based products where the iron, iodine, and chromium content is near or slightly above the RDE. So only these could be considered as well supplementing. These products could be considered as well supplementing the trace elements. When people take trace element tablets plus these algae, they are probably above the recommended daily intakes for quite a number of elements. And that is one of the things what needs to be considered when dealing with nutraceuticals, that quite a few people not only take one of them, but they want to do good for their health. And it's claimed in the press and in the internet, on the internet, that it's good for your health when you take these things, that they may overdo it. For the non-essential elements, cadmium is regulated in the EU as maximum 1 milligram per kilogram. In seaweed-based materials, it's maximum 3 milligrams per kilogram. The ANSI, the American National Standards Institute, did I get it right? I think so. Has a maximum of 0.3 milligrams per kilogram, and that recommends an intake of less than 6 microgram per day. There is none of these studied nutraceuticals comes near the cadmium level. So cadmium isn't a problem for any of these food supplements, sorry. And there is one of the algae-based products was found to be near the value for the raw material, but not anywhere near the value for the daily intake. For the lead, that is as well recommended food supplements, 3 milligrams per day, per kilogram total. The Americans have a maximum of 10 milligrams per kilogram and a daily intake of less than 20 micrograms. No maximum recommended daily intake is existing because lead doesn't have one. As far as we know, none of these is coming near the regulation limits. So lead is as well not a problem. And for the arsenic now, what is one of my favorite elements is due to its rich organic chemistry, we still don't know all which are available by nature. There might still be quite a number of them unknown. The problem is there is no regulation in the EU for nutraceuticals for arsenic, either total or inorganic. China has regulated the inorganic arsenic to less than 0.3 milligrams per kilogram. And Australia has a regulation for seaweeds, which says it's less than 1 milligram per kilogram seaweed. Daily intake is recommended to be below 10 microgram. When you look at the totals, daily intake is here in microgram. There are quite a few which are seem to be relative high. Again, algae, and in this case, the krill oil, whereas the fish oil predominantly is at least a factor of 10 lower. What was a bit astonishing for me because krill and fish oil both are marine based. I thought they are very similar at the beginning, but okay. And the thing is, when you look for the inorganic arsenic, the problem is you have a very large number of arsenic containing compounds with a high variability of toxicity. The inorganic arsenic is pretty toxic. The hydrocarbons, the fat-soluble arsenic compounds have been found relatively recently to be highly toxic. And the organic ones, like the dimethyl arsenic acid, there's some intermediate toxicity, and others are unknown toxicity or non-toxic. In addition, inorganic arsenic is a class 1 carcinogen, so it's not that advisable to take up too much of it. How to determine this is one of the options is using hydrogenation from solution without any separation. Another option is to use standard HPLC, ICP-MS, or any other suitable detector. ICP-MS is the standard one with non-ion exchange column. And there are other forms available, for example, measuring total arsenic after extraction and back extraction. We've opted here for option 1 for the hydrogenation in our case, because with the oils, I didn't want to ruin an anion exchange column, getting some oil residues onto it. And then when you look at these values, the distribution is the same as for the total beforehand of the different supplements. Some of the algae are pretty high as well. The krill oil contains relative much, and there suddenly as well a couple of fish oils start to appear. So really, one of the things one has to keep in mind, especially with the oils, that some of this inorganic arsenic which comes out here might be coming due to hydrolysis of organic arsenic, which can't be completely excluded so far. Some arsenic containing esters might be a possibility, but it's not clear yet. So 3 of these algae-based products, they are kelp-based products, that inorganic arsenic is above the Chinese and Australian limit. And one of the garlic-based products was above it. With regard to total inorganic arsenic. So one has to, with arsenic, one has to really distinguish between total arsenic and inorganic arsenic, because the total arsenic, when you remember, that was at least an order of magnitude higher than the inorganic one. So to summarize, the daily intake is practically nearly always below the regulation limit for the non-essential elements. Algae contain more than the other kinds of nutritional supplements. Only the algae-based supplements contribute significantly to the daily element intake. Fish and krill oils, when you supplement them in addition with trace elements, you're not going to get into trace elements in reasonable quantities. You're not going to get into problems with regard to overdosing on trace elements. And but that can be a problem with when you do that with algae-based supplements. And fish oils are contain relative small amounts of inorganic arsenic in contrast to krill oils, which are higher. Thank you very much for listening and for the people who did quite a bit of that work.
Andrea, thank you. That was really interesting, especially the bit about the arsenic, which is also one of my favourite elements as well. Okay, so we are going to stay with arsenic for our next presentation.
Where are we? Sorry.
It's okay. You just have to turn off.
Yeah. Yeah, that one. So,
super. Okay.
Sorry.
It's okay. So if we If our third and final presentation this afternoon is Dr. Panayot Petrov from the National Measurement Laboratory at LGC in the UK. Panayot obtained his degree from the University of Sofia in Bulgaria, and then he undertook a postdoc at Trent University in Canada in Ontario. Panayot has worked at the LGC since 2011, where he works today as a science leader and a lab operations manager. He has extensive experience in speciation and elemental analysis, as well as single particle analysis, and he works in the core metrology and high accuracy speciation team. Panayot's presentation today is entitled Accurate Determination of Inorganic Arsenic in Rice by using a novel LC-ICP-MS calibration strategy. Thank you, Panayot. I ask you to share your screen. Great, that's perfect. It's over to you.
Jackie, you just need to unmute Panayot.
Sorry,
You can-
let's have a look.
I think I can.
Okay, is that?
How about now?
Okay, can you hear me?
Sorry about that.
Lovely.
Okay. Thank you for the kind introduction, Jackie, and for giving me the opportunity to present our research in front of this audience, which I think it's a great research, great new calibration strategy that provides high accuracy and low uncertainty measurement and suitable for speciation analysis. And today I'm going to demonstrate you the power of this calibration strategy for the determination of inorganic arsenic in rice. Try to. Yep. I will start my presentation with a bit of background information. Why do we need to determine inorganic arsenic? Arsenic is an element that is spread all over the world, and it is present in all the environmental compartments, being air, water, and soil. And from there, it enters the food chain in different levels depending on geographical location. It's already been mentioned in the previous presentation, the toxicity of arsenic very highly depends on its chemical form, with the inorganic arsenic being more toxic than the naturally present organic forms like MMA and DMA. There are a lot of negative effects from arsenic. It is known to impact growth rate, immune system, which also increases the risk of illnesses. It's known cancerogen, and it is a reason for a number of other diseases, for example, the Blackfoot disease. The problem with arsenic in rice is that, first of all, mostly the inorganic forms of arsenic accumulate in this food. And in addition, it is estimated that about 1/5 of the world consumed food daily is either directly rice or rice products, which means that this represents a major risk. Having this in mind, in 2015, the European Commission came up with a regulation that is regulated the maximum amount of inorganic arsenic in variety of rice products. Recently, similar regulation came into force in North America as well, basically mimicking these levels. And the amount of permissible arsenic in the different rice products depends on the type of the rice, being the highest for the brown rice and the lowest for the rice that is intended for baby food production. The problem with determining inorganic arsenic in rice, there are actually two major problems based on separation issues and quantification errors. And we need to be able to accurately determine inorganic arsenic to be able to enforce these regulations. So the analysis have to be accurate, traceable, and really defensible in order to be able to enforce these regulations. In terms of separation issues, like Andrea already mentioned, most often for HPLC ICP-MS, the column that it is used is anion exchange column, and there are problems with species coelution. For example, the first two peaks that you see on the top chromatogram. This is just before 1 minute retention time. They're arsenic free and DMA, which coelute. And inorganic arsenic is defined as the sum of the species of arsenic free and arsenic 5. So in this situation, a quantification error can come from the fact that species coelute. In addition to this, there are in many cases species transformation, which can also lead to erroneous results. In terms of quantification errors, the problem comes from there are a few problems. Unfortunately, arsenic is monoisotopic element, and the species-specific IDMS, which is the gold standard for accurate analysis in speciation, is not applicable for this element, and of course for its species. Additionally, the sensitivity is strongly affected by some matrix components, for example, the well-known charge transfer effect in presence of carbon, in eluent most often. Also, in many cases, there is significant detector sensitivity drift. And in such cases, you see example on the right. In such cases, if just an external calibration is used, this will result in biased results. In most cases, internal standardization is used to correct for this sensitivity drift, but the problem comes from the choice of internal standard. First of all, the element of choice should not be present in the sample. Selenium, for example, is really good internal standard for arsenic, but in many cases where we analyze food, where there is arsenic, there is selenium as well. In addition, it is not only the element of choice, but the species of choice, because it is well known that the different species have different sensitivity and also react different in terms of drift with time. And there are different options using continuous or discrete internal standardization. But in any case, there will be no element or species that will have the same chemical and physicochemical parameters as our analyte. Also, matrix effects. The usual practice to correct for matrix effect is to use the method of standard addition. Unfortunately, this is not always applicable for correcting matrix effects. For example, when the matrix effect is superimposed by the strong drift, if we're using method of standard addition, we will obtain even more biased results compared to if we have just used the external calibration. To correct for all these problems, we developed this calibration strategy that we call on-column internal standardization, and we are using it for high accuracy speciation analysis. The principle of this strategy, it is detailed in a recent publication. Reference for it you can see at the bottom of the screen. But in summary, if we think about standard liquid chromatography ICP-MS setup, we are having the HPLC pump followed by the separation column, and the output of the column goes to the ICP-MS. For our strategy, what we do is just basically just before the entrance of the column, we are putting a 6-port injection valve. Two of the ports of this 6-port injection valve are basically connecting LC, the separation column, and the ICP-MS, and the other 4 are connected this way that by using a low pressure pump, internal standard is continuously fed into a fixed volume sample injection loop. And after a certain time, that we call it time buffer, the valve is switched, so the content of this injection loop is injected into the column. So this gives us the opportunity to use absolutely the same species that is our analyte as internal standard, because we artificially move it in the chromatogram with time. The advantages of this calibration strategy is that it is based on chromatographic injection of the same species of the analyte as the internal standard. It can compensate for on-column losses and also for really, really strong drift effects that are really quick. It can be applied to absolutely any detector that is capable of recording time resolved data. It doesn't need to be mass spectrometer. It can be AAS, AFS, or OES detector. And it also is applicable to different type of chromatographic separation, being gradient or isocratic elution, and more than one species can be quantified with with this approach. In terms of limitation, since we are injecting another compound into the chromatography, it requires really good chromatographic resolution, and additional hardware might be needed. Although this is not really necessary, this 6-port valve and external low pressure pump that I mentioned in the previous slide, and if we have time, we can also discuss this. In terms of applicability, on this slide, I'm showing you an example how a chromatogram will look. This is just injection of arsenic 5 standard and internal standard, just to demonstrate you how it will look like. And the ratios between the standard and internal standard that were investigated were between 1:4 and 4:1. And in all cases, excellent recoveries were obtained, being between 99.5 and 109%. With this approach, we can compensate for really strong drifts, like it's demonstrated on this slide. And the reason for this is that, again, the analyte and internal standard are the same species. There is absolute no difference in their physical-chemical parameters, which makes this approach of internal standardization really the ideal internal standardization. It is absolutely independent if the species is present in the sample or not. So it can be applied for blanks or for high content samples, and it can compensate significant positive, negative drifts, linear or non-linear, with ultimate correction accuracy. As you can see on this slide, there are many cases that sensitivity drift was significant, more than 15 or 20% in some cases. And if external calibration was used, the same percentage error would be made. But using this type of internal standardization, the variation of the ratio between the analyte and internal standard was really small. As you can see, it varied around 5%, and this is based on single injection. But if we average, let's say, 3 ratios, this is really within less than 1% variation with this strong sensitivity drift. This example how it can be applied to quantification of different species with different chromatographic separation. For example, in this case, we quantified monomethyl arsenate and arsenic 5 with isocratic elution, that is on example on the left, or with gradient. This is the chromatogram on the right. And this calibration approach, we finally applied for the determination of inorganic arsenic in rice by using exact standard matching quantification. The workflow for this analysis, we've done extraction similar to what Andrea showed by using of diluted nitric acid and peroxide, thermostatic conditions for 4 hours extraction. So we're taking half a gram of rice. We subject it to this extraction procedure. Then we adjust the extract to pH 9 just to be compatible with the chromatographic separation we are using, which in this case was using anion exchange from column PRPX 100. And finally, the measurement was done by tandem mass spectrometry in oxygen mode with the mass shift of from 75 to 91 adduct to avoid some interferences, for example, the famous argon chloride interference on arsenic. The quantification, like I mentioned, was done with exact standard matching, bracketing calibration, which basically is approach where we inject in sequentially standard sample, and so on. And in the end, after the analysis is done, it follows peak integration, and we calculate the ratio between our analyte, arsenic 5, like you can see on the chromatograms, and the internal standard. And we do the same for the calibration standard between which our sample is bracketed. And finally, the inorganic arsenic concentration is calculated against this calibration standard by using the equation that you're seeing on the top of the screen. So in this equation, we need to know the mass fraction of the calibration standard, and we need also the calculated ratios between the peak areas of the analyte and internal standard in the sample and in the calibration standard. But also, what comes into the equation are the volumes of the injected sample and standard and internal standard. However, since we are using external 6-port valve with fixed volume sample loop, these volumes that are in red orange color, that are the volume of the internal standard in the sample on the top and the calibration standard on the bottom, they cancel each other because they're the same value. In addition, because we're injecting the same amount of sample through the HPLC and the same amount of calibration standard, they cancel as well. So in the end, we end up with the equation that is on the bottom, which is dependent only on the mass fraction of the calibration standard and the calculated peak area ratios for the sample and the calibration standard. However, if we want to calculate the measurement uncertainty, we cannot ignore the contribution of these parameters. So they're kept in the equation, although their ratio is 1. And finally, the uncertainty, the combined uncertainty is calculated by the second equation that you see on the screen. With a recent example for quantification of inorganic arsenic in white rice, the concentration of arsenic at the instrument was about 2 micrograms per kilogram with the uncertainty of 0.04, or this gives a relative combined uncertainty of about 2%, which is absolutely great for speciation analysis, and we have accounted for all the possible contributions from the measurement uncertainty. Usually for people who are doing speciation analysis, they know that with external calibration or even when internal standardization is used, usually the overall combined uncertainty from the measurement is above 5%. In our case, it's usually below 2%. On the right-hand side, you're seeing a pie chart of the different uncertainty contributions. Looking at the uncertainty budget, more than half of the uncertainty contribution, so more than 1% in total, comes from the calculation of the peak ratio between the analyte and internal standard in the sample. And the other major contributors are the concentration of the primary calibration standard, although we are using a primary standard from National Metrology Institute, which have really, really low uncertainty, but still with this overall so small uncertainty of only 2%, this becomes a significant factor. And finally, the uncertainty of the volumes, they're negligible. They contribute to about 4% each. The method trueness and measurement uncertainty was estimated with this method for a variety of samples. In this case, we analyzed some baby rice material, baby rice samples. This is food purchased from UK market, and so you can see the concentrations obtained. In this case, we had a bit above the legislation limit concentration of inorganic arsenic. And in all cases, for these samples and for the two reference material, the brown and the white rice that are at the bottom, the overall measurement uncertainty in all cases was below 3%. And excellent recoveries were obtained in all cases around 100%. The additional sources of uncertainty for the whole measurement, for the whole analysis, they come from repeatability, and we also have a component of intermediate precision. This was estimated by analyzing 3 different rice samples with varying concentrations. So from these 3 test materials, 3 subsamples were taken each time, and this was done on 6 batches above 1 month apart. And I have to highlight here that for the results that you're seeing is not only coming from the method itself, this variability, but also the material homogeneity has effect on the obtained value. Moisture determination, usually the contribution of this factor towards the uncertainty was very low. In this case, 5 to 10 to minus 3%, considering that in rice, the moisture content can be quite high, and we've seen values up to like 15% moisture. Sample dilution, this is negligible component to the overall uncertainty. Oh, excuse me. Okay, next slide. Yeah. So in conclusion, I hope I successfully convinced you that we develop a novel calibration strategy that offers high accuracy speciation analysis for speciation analysis with really low measurement uncertainty. As the internal standard species are the same as the analyte species, it offers a very attractive alternative to IDMS calibration and compensates for most of the negative effects which IDMS can compensate for. including matrix effects, signal drifts, and potential on column drifts. The good advantage of this calibration strategy is that we do not need to use mass spectrometry, and therefore it is applicable to monoisotopic elements. The method also can be employed with any detector that can measure time-resolved signals. And with this calibration strategy that we develop, it is suitable for high accuracy analysis with total expanded uncertainty with coverage factor of 2. That includes homogeneity, moisture correction, etc., of below 5%, which makes it a really good method for assigning reference value and for certifying reference materials. Respectively, the relative uncertainty that comes just from the calibration itself has been between 2 and 3%. This is expanded measurement uncertainty in the range between 60 and 300 milligrams per kilogram of inorganic arsenic in dry rice product. The proposed method is currently used for certification of reference materials and in support of the European registration for the maximum amount of inorganic arsenic in rice and processed rice products. With this, I would like to thank my colleagues who contributed for the research that I present you here, that you see here on this slide. This is Christian, Lee, Sarah, and John. And I would like also to thank BASE for sponsoring, for funding in part the research I presented here. And I would like to thank you for your attention and invite you for a discussion after we finish with this session. Thank you.
Okay, Paniot, thank you so much for that. Can I ask the other presenters if they would come back on camera, if that would be okay? Everyone in the audience should be able to unmute themselves if they would like to ask a question. So far, there's not been any questions come through. You can put up with my crappy questions for a little bit, if that's okay. And they're not very exciting, but I've got them. So I do have one. Okay, we'll start with Sonalika. I was just wondering, it was a really interesting overview of what goes on at RSSL, and I was just wondering if you could tease out a little bit of the work you're doing on the titanium nanoparticles that you mentioned in food.
Sure.
And especially bearing in mind that the EU in 2022 will stop adding titanium dioxide as a food additive.
Absolutely. Yeah, so actually there are quite a few countries that have, some countries actually now that have already banned titanium dioxide as a food additive. So titanium dioxide was just an example of, you know, one type of nanoparticle that we are actually looking into. You know, we've partnered up with a few companies that are investigating nanoparticles and looking at characterizing them, both in the food and the pharmaceutical side, actually. And we're looking to help them quantify not just the size of their nanoparticles, be it titanium dioxide or any other composition, but also look at the mass fraction of the nanoparticles. How much of your, in this case, how much of the titanium is in the titanium dioxide format as nanoparticles, or how much of it is actually there in solution. So it's quite a powerful technique for you to be able to find that percentage. And yes, titanium dioxide is going to be banned, but there are a whole host of other nanoparticles, and, you know, moving with nanotechnology, you know, progressing at such a high pace. You look at iron oxide. Iron oxide is also used quite frequently, although it can be a bit challenging because of the light nature of iron and interference is present. But single particle ICP-MS in combination with some of the other more established techniques like SEM and DLS, they're actually very, very powerful, all of these techniques, when it comes to even novel food submissions. So we're doing a lot of work around helping clients look at nanoparticle assessment for regulatory submissions. So although EFSA at the moment is only accepting SEM and imaging techniques for submissions, hopefully in the future that they will open up to looking at a wider range of techniques like single particle ICP-MS.
And so when you do single particle ICP-MS for titanium, how do you prevent the agglomeration, or how do you come at peace with, well, they would agglomerate naturally anyway, so where do you stand with that?
So as if any of us has actually worked around in the nanoparticulate field, you'll know how difficult it is to know whether I can see Panayoot nodding there, how difficult it is to know whether you've got the optimal dispersion or not. I mean, we've conducted several studies here with looking at sonication times and sonication energies. And, you know, I brought the EFSA example in, and they've got like a range of sonication energies that they recommended from low to high. You subject your sample with that sonication energy, depending on how your sample interacts, how your titanium dioxide interacts with the rest of your matrix, rest of your components. Your sonication energy can either, you know, dissolve your sample, or it can successfully deagglomerate it, or successfully or not successfully deagglomerate it. Yeah.
It's one of those chicken and eggs. You don't know whether you're.
It is. Yeah. So it's a tricky one. I think using different surfactants, maybe some salts and sonication energy. It really is. I
think it shows the benefit of using a collection of techniques.
Absolutely.
Because not one technique is going to give you the answer. Well, thank you for that.
No problem.
Excellent.
Thank you.
Andrea, so we'll stick with arsenic, I think. That's the only element worth talking about.
Why, I'm not surprised.
Wow. So I Googled what on earth krill are while Panayoot, I was listening, I promise, but I Googled what krill are. And I was thinking, wow, goodness, this is because they had lots more of everything that compared to fish oil, and fish oil might be cleaned up a lot more, like you said.
Yes. Fish oil is much more cleaned up than the majority of krill oil samples were at that time, at least. Sure. Potentially the industry has improved or changed their procedures to make that. At the moment, I haven't looked in the last year, so I can't tell.
I mean, I was just really alarmed at how small they are. To say that they're basically sponges, and I was just goodness.
As long as you don't tell that to a biologist.
Sure. Well, and I also learned they can live up till they're 10 years old. I was thinking, because it's a lot. I was already going, wow, they're really small. They're sponges for arsenic and lots of other metals, and they can't possibly live very long, but they can live on average 2 to 6 years.
They live in the Antarctic, where life is a lot slower.
Yeah, no, that's true.
At least the majority of them, where they harvest them. I mean, krill or relatives of krill live in all seas.
Okay.
But that what we know as krill and what is used there for these supplements is harvested in the Antarctic. That's the stuff normally the whales and the penguins eat.
Yeah. I mean, I think the take-home message is to stick with fish oil if you need to. Well,
might be a good idea. Yes.
Yeah. Thank you. Panayoot, we've got a question for you. It says it's from Jorg. And Jorg asks, thank you for a very fine presentation. One query, however, you mentioned that the on-column calibration can also be used for gradient program. I have some doubts that this would be possible for all gradient elution programs, especially when methanol water mixtures are used, since the standard is eluting off at a different time than the analyte, but maybe I misunderstood.
Yes, this was one of the concerns, and that's actually what we checked when we developed this method, and it does work. The reason for this is that the only thing that matters is that they always elute at the same condition, the standard, I mean the analyte and the internal standard. And Jorg is right, because, and that's what we tested it with, 5% difference in methanol content, and there was difference in the species sensitivity. But because it always elutes at the same time with the same sensitivity, the ratio remains constant despite the drift of the instrument. And we had at this particular time, I think it was about 15% drift during the course of the analysis. And still this approach corrected it really well. And in the end, we obtained results within 2-3%
Okay.
from each other.
And did you compare I mean, your method is a game changer because it just allows an internal standard for species that we don't have internal standards for. You know, I get that. But did you, just to give us mere mortals an idea of our error and how wrong we are? Did you compare another, like your normal method before you started doing this? Did you compare, and could you give us an idea of what the differences were for us that just, you know, use germanium as an internal standard?
No, I have not tried this for speciation. We can do this by post-column continuous introduction of germanium. But I can tell you what was the error with external calibration. So we developed this method not only because we are curious for science, which is the case, but because we had a problem. And the problem was with this terrible drift that we got. If you have drift of 15% and you're using external calibration, the error that you will be making is 15%. That's it. That no exception here. You can use different calibration strategies to correct for the drift. For example, if you frequently inject calibration standard, continuous calibration verification, you can call it if you like, and you use this response to correct for the drift, you can do it to some extent, but still the efficiency of this is not as good as if you can do it with the same species in the sample itself.
No, absolutely. It was really interesting. That's it. That's all the questions I've got, and that's Jorg's question.
And I'll have one to Panos for the discussion, just for the fun of it. Panos, do you think really that a drift like that what you showed is common, or is that more something specific for your lab or your instrument? Because to be honest, I've done quite a bit of arsenic speciation. Yes, your approach will certainly work nicely when you have a sample which contains only 3 or 4 arsenic compounds. But when you work with samples which have 10 or 20 compounds, then you are in big trouble, because then you may not find the window where you can place your standard in.
You're absolutely right. This is the limitation of the method, like I mentioned, that you need to have space in the chromatogram in order to place it there. You can very precisely do the timing and put it where you see a gap. But sometimes, like you say, if you have really complicated chromatograms with multiple species, thioarsenates and some others that basically are next to each other, what you can do is basically delay so much the injection that it goes to the end of the chromatogram. It is still useful, but it is not much of a difference than the traditional post-column injection approaches.
Exactly. Then you can do it just as well post-column or before your sample.
Exactly. The only advantage here to the post-column is that you're passing it through the column. If you have any on-column losses due to conversion or absorption or something like this, you can correct for this. Or if you have spitted plicks because of something else elutes where your analyte elutes. So this is the advantage in this case, which is sometimes it's not a small advantage, but the more complicated chromatograms you have, the less powerful is this technique in terms of advantages over other calibration approaches. And in terms of drift, I have to say that unfortunately, yes, we do have these drifts, and we noticed that we tried with different instruments, triple quad, single quad, and different columns, different elements, and there is always some drift. It is most significant in the beginning of the analysis, the first like 2-3 hours, and then it basically levels off. Unfortunately, or fortunately, the method that we developed now, it takes 5 minutes for sample injection. So we either have to run the instrument for 3 hours doing nothing just to have a nice stable signal, or we inject our sample in the highly drifting region, where if we don't use this approach, basically the results will be quite biased.
Mm.
Yeah. Sonalika, I have one more question for you, if that's possible.
Of course.
Sonalika, nice talk. One question: have you ever found hexavalent chromium in a food sample?
Have I? So That's a good question. I've never
Or your
looked for
lab.
it.
We're interested in-
Yeah. No, so we don't tend to do a lot of speciation. So we haven't actually looked for any hexavalent chromium. So I couldn't answer that for you. But if we do find it, I shall let you know.
Well, or if you need a reputable lab to do speciation for you, some of us are
Absolutely.
on the call.
Absolutely. Absolutely. Yeah.
Excellent. Okay. Well, thank you everyone for today, and thank you for joining. I'm going to share my screen just a second to remind you all that we have BNAS next year. So thanks all for joining us this year for all of these virtual seminars and being very patient with us as we've navigated our way through the technology. We're trying to keep moving on with this. We've got some ideas for all the other letters in the alphabet. But if you've got any suggestions or presentations that you'd like to request or you'd like to give, please could you get in touch with myself or Sarah? I've put our email addresses on there. The next virtual session will be in February 2022, and that will be G is for geochemistry. So again, if you've got any ideas or anything you'd like to hear about, just give us an email. And we're finishing and firming up our plans, although as you'd imagine, they're all ever changing, for the 20th BNAS conference in Manchester next year, which is our postponed event from 2020. The plan at the moment is to have this as a face-to-face meeting and bring together some familiar faces to help us celebrate the 20th BNAS. We will keep you updated with that, and we'll circulate the information in the normal way. But again, if you've got anything you want to ask me about that, just drop us an email. I'd like to wish you all a very safe and healthy end of 2021. And hopefully we'll see you again in February for G is for geochemistry. Thank you all for joining today.
Brilliant. Thank you very much, everybody.
Thank you,
Thank you.
all of you. Goodbye.